Do you enjoy eating ripened mangoes? Do you know the gaseous hormones released from the ripened or injured fruit is responsible for the ripening of raw fruits? Now, can you tell me which gas is this? Well, this is ethylene gas, which is an unsaturated hydrocarbon. In this video, we will discuss one of the unsaturated hydrocarbon, that is alkene. Alkenes are unsaturated hydrocarbons which contains carbon-carbon double bond in their molecules. Alkenes are also called olefins, which means oil forming. Ethene, the first member of this family, followed by propene, butene and so on. Now, let's discuss the structure of alkene. The carbon atoms involved in the double bond are sp2 hybridized. Thus, carbon-carbon double bond in alkenes consists of one strong sigma bond due to head-on overlapping of sp2 hybridized orbitals. Now, one pi bond obtained by lateral or sidewise overlapping of two p orbitals of the two carbon atoms. Do you know the pi bond, which is a weaker bond due to sideways overlapping between the two p orbitals? Therefore, alkenes are easily attacked by an electrophilic reagent or compound which are in search of electrons, as alkene behaves as source of loosely held mobile electrons because of presence of pi bond. Now, let us look at the nomenclature of alkene. First, let's recall the IUPAC rule of alkene nomenclature. First is to identify the longest carbon chain. Then, the numbering is done from end, which is nearer to the double bond. Then, the suffix ene, that is ene, replaces ane of alkanes. Let's find the IUPAC name of a few compounds. In the first structure, which is given here, there are 4 carbon atoms and the double bond is between the first and the second carbon atom. So, the IUPAC name of the compound will be but1-ene. And in the second structure, the double bond is between the second carbon atom and the third carbon atom. Therefore, the IUPAC name of this compound will be but2-ene. Let's discuss isomerism in alkenes. Members of the alkenes family exhibit both structural and geometrical isomerism. Alkene shows chain as well as position isomerism, which are the type of structural isomerism. Let's take an example of a compound with molecular formula C4H8. This compound can be represented in 3 different ways. That is but1-ene, but2-ene and 2-methylprop1-ene. Here, structure 1,3 and 2,3 are examples of chain isomerism, whereas the structure 1,2 are position isomerism. Now, let's have a look at geometrical isomerism in alkene. In alkene, the geometrical isomerism is because of restricted or hindered rotation about carbon-carbon double bond. In case the carbon or group attached to the double bonded carbon atoms are to rotate about or to exchange their position, they can do so by breaking the pi cloud. For this purpose, 250 kilojoule mole inverse of energy is needed, which is not available at the room temperature unless supplied from an outside source. In other words, we can say that the rotation about the carbon-carbon double bond is restricted or hindered. As a result, the organic compound of the type C2A2B represents 2 special arrangements for isomers and are called geometrical isomers. The isomers, which are similar atoms or group, present on the same side of the double bond are known as cis isomers. On the other hand, the isomers which has similar atoms or group opposite sides of the double bond is known as trans isomers. The cis and trans geometrical isomers can be distinguished with the help of certain physical characteristics such as dipole moment, boiling point and melting point. For example, the dipole moment of cis isomer is normally higher than that of the trans isomer. Here, the dipole moment of cis but2-in is 0.33 dBi, whereas dipole moment of trans form is almost 0. Therefore, we can say that cis form of alkene is found to be more polar than the trans form. Next, the boiling point of cis isomer is slightly higher than that of trans isomers, because in cis isomer, the magnitude of dipole-dipole interaction is higher, whereas the trans isomer usually has high melting point than the cis isomer on account of symmetrical structure and more compact space. Now, let's discuss the preparation of alkene. Alkenes can be prepared from alkynes, alkyl halides, vinyl dihalides and alcohols. First of all, we will look into the preparation of alkene from alkynes. Alkenes can be converted into alkynes as a result of controlled oxidation in two ways. The first is by the use of Lindeler's catalyst, which is partially deactivated palladized charcoal. And the second is by the action of sodium in liquid ammonia. Reduction of alkene to alkyne by Lindeler's catalyst gives a cis alkene, while the same with sodium in liquid ammonia forms trans alkene. From alkyl halide, alkenes are formed by the elimination reaction. An alkyl having beta hydrogen is heated with alcoholic solution of KOH. As a result, a molecule of hydrogen halide is eliminated to form alkene. This reaction is called dehydrohalogenation reaction and also the beta elimination reaction. Next, the preparation of alkene from vinyl dihalide. Dihalides, which is two halogen atom that is attached to adjacent carbon atoms, are known as vinyl dihalides. Vinyl dihalides on treatment with zinc metal loses a molecule of ZnX2 to form an alkene. This reaction is known as dehalogenation reaction because only halogen atoms are removed. Alkene can also be prepared by monohydric alcohols or alkanols by the loss of molecule of water. Since water molecule is eliminated from alcohol molecule in the presence of an acid, the reaction is known as acidic dehydration of alcohol. For the dehydration, the presence of beta hydrogen in alcohol is necessary. As you can see here, beta hydrogen along with OH group, which is attached to the alpha carbon atom, has been eliminated as water molecule. Now, we have come to an end of this session. Can you tell propene obtained from partial reduction of alkene using Lindeler's catalyst will show geometrical isomerism or not? Well, think for the reason in support of your answer. Now, let's summarize what we have learned.
Manorama Horizon. Learning made simple.